at the sunset time. So that means there is a stimulus which actually execute some of the motions. So by that stimulus, which is a sunlight in these cases, I can have a change in dimension. So this is basically 4D. So some 4D is something which is repetitive in nature under the effect of some stimulus. Actually, there is no not a fourth dimension. This is the part is, let us say, expanding, or it is compacting as a function of time under the effect of some foreign stimulus. So if I do this for my 3D printed part, we call it as a 4D printing. Right now, taking a specific example from the mechanical engineering viewpoint, if you see in typical mechanical manufacturing, we are interested in measurement of the forces, and for the measurement of forces we use a dynamometer, right? So in a dynamometer we normally use a piezoelectric based transducer, like, which is a quartz crystal, right? So but this quartz crystal has a very typical behavior. When I apply a load over a quartz crystal, it changes its dimension. Now you release a load, it will come back to the original position. So if I do this exercise, applying a load, releasing a load, applying a load, releasing a load, and I do this for n number of times, I got a same displacement. And that this change in dimension or change in length is calibrated for the force measurement, which is digitally displayed on my instrument, right? So my submission is, if I, let us say, print the quartz crystal, and yes, please, is it audible? Audible, please.
Yes, sir.
Okay. So in simple words, if I print a quartz crystal, 3D print a quartz crystal, I can actually use this for the measurement of forces. Now, another example, in typical polymer 3D printing, we have a polymer called PVDF. If you just see the chemical chain of the PVDF, I have a carbon-carbon chain, and on alternative carbon chain, hydrogen and fluorine atoms. Carbon chain, all covalent bonding, and on each carbon, successive carbon, I have a hydrogen, I have a fluorine, I have a hydrogen, I have a fluorine. Now this is called the alpha phase, right? Now what I do, I apply a load. The load application means a physical load, or in electrical terms, this can be a high voltage. So when I apply a load, maybe the physical load or maybe the high voltage, so what will happen? All the hydrogens are aligned to the one side of the carbon chain, and all the fluorine on the other side of the carbon chain. Now this is called beta phase, right? Now what happens once the material is changing from the alpha to the beta phase? There is a, hydrogen has a typical behavior of 1h1, right? So there is a development of the van der Waals forces, because of which we will express the compaction, right? Now you release the load, it will again shift from beta phase to alpha phase. Again we will have a expansion, right? So I can basically control the compaction and expansion by changing the material from alpha phase to the beta phase. So in simple words, if I 3D print a PVDF based substrate and apply a load, release a load, apply a load, release a load, I can quickly change it from alpha phase to beta phase to alpha phase, and the process is unlimited for n number of times. And then I can make a basically a transducer which can be working similar to what I am getting through a quartz crystal, which is actually available in nature, right? So in simple words, the printing of smart material is recognized as a 4D printing. Now this smart material, of course, needs some stimulus. The stimulus can be load, the stimulus can be temperature, the stimulus can be electric field, stimulus can be magnetic field, and there can be, combination of stimulus also. So in other words, this 4D printing is an extension of the 3D printing, or the, different additive manufacturing processes may require a different type of stimulus. And one important thing is the process is repeatable. So I should come back to the original situation, right? So 3D, any 3D printing becomes 4D as a function of time. So the fourth dimension is basically the change that we see because of the stimulus itself. Now, what can be the reason of the smart behavior? This can be the intrinsic property of the material, like the internal property. Like I have given the example of the PVDF crystal. So in PVDF, I have a alternative carbon-carbon chain, then hydrogen and fluorine. You apply a load, it will change from alpha to beta. Release a load, it will come back to from beta to alpha. So this self-expansion, self-contraction is because of the inherent behavior of the material. So we will call it as the intrinsic property. Right? Sometimes we want to add property into the material. Like so that is basically extrinsic property. So this is depending upon some factors like how much the reinforcement you can do. Like for example, most of the polymers they are insulators, and if you want to make them conductor, you have to do the reinforcement of some metallic powder. Like we can think of a reinforcement of copper powder, aluminum powder, graphene powder, right? So with the reinforcement, even I can make some of the insulator as a conductor. So this can be the reason for smartness. Then there is a new area that is called metamaterial. Now this is actually really important and has a lot of meaning, specifically in the metal 3D printing. This meta structure or meta materials, these are maybe some new words for a mechanical engineering background people. But typically in civil engineering and in electronics engineering, people are using this meta structure or meta material in a big way. Like to understand this in a simple way, take the example of a railway bridge. In a typical railway bridge, whenever we were used to explore about this railway bridge construction, so in our strength of material class, we were reminded about the trusses, right? So in truss, what is important? The length of the link and the angle of the link. So total, let us say the young modulus that is coming for that material is not because of the inherent property of the material, but is dependent upon the length and the angle of the link, which may be able to capable of giving the same property or the better property than the solid structure. So based upon this, even we can have a hollow sections or much lightweight section as compared to the solid sections, specifically in case of the railway bridge. So these metamaterial structure are really important when I am going for the implant design, because I want to keep the 3D printed component as light as possible, high strength to weight ratio I want, and I want that osteoblast cell should grow in a good way. So for these type of capabilities, the metamaterial has a lot of meaning, specifically in the 4D, because I will be able to manage the modulus of toughness and young modulus in a much better way as compared to the solid section, right? Then there is a an area in 4D, specifically where I have to program these materials. This type of programming is really important. So broadly, this particular picture I have taken from the Hager et al. Paper published in 2016. It is broadly explaining about the type of the programming. So this is of three types. The first type is called one-way programming. The first type is called one-way programming. Like my material is in the state A, I give some stimulus, it goes to the state B, right? The stimulus can be temperature, the stimulus can be current, the stimulus can be magnetic field, stimulus can be humidity, stimulus can be some chemical reaction, it may be some thermal, something like that. But once I have shifted from state A to state B under the effect of stimulus, right? Then I give another stimulus, it comes back to the state A again. So this is called one-way programming. I'll give one simple example to understand this. Just imagine you are in some heritage building now, and you are interested in the preservation of such type of the structure. Now how my structure is going to damage because of the environmental effect. So one of the environmental effect on my structure is because of the, let us say, the acid rain, right? So what is acid rain? Acid rain is basically a carbonic acid, H2CO3, which may damage some of the pores, and the cavity size that cavity size may be distorted. So that is actually the problem with this type of the acid rains. Now just imagine I have thought of some solution which can be some coating or some filling of cracks for these type of the heritage structures. Now I have put the effect of the acid rain just in the lab environment. I am checking the what is the effect of the carbonic acid, right? So let us say I change the physical state of my structure, right? Now I again want to get it back to the original position. So what is the another stimulus? The most common stimulus for these type of environment is the high temperature. Suppose there is a sunstroke over there. So what will be the effect of heat? If I am able to get it back to the state A, this is a typical example of one-way programming, right? And people have reported large number of papers specifically for the 4D behavior as a one-way programmed material, development of one-way programmed material for the 4D printing application, specifically in the area of the heritage structure. A lot of sensing capabilities can be added with these type of things. Then there is a two-way programming. Specifically in two-way programming, we have a very good example of effect of the electric field or the magnetic field. Like for example, my material is in state A, I want it to on a state B. So let us say the stimulus selected is a magnetic field. So I switch on the current, which will basically changing the magnetic field. So let us say there is some change. Then you switch off the current and it will come back to the original position. So this is two-way programming. Like for example, in my room there is a fan. So I have a regulator knob with me, and with the help of which at different knob position I can have a control over the RPM. So I can have a high RPM, I may have a low RPM. So this is typically a two-way programming. Now typical application, just I want to share to you. In orthopedics, we got some good number of cases here in Chandigarh in PGI, like because of the some accident or because of the birth defect, some person is having a unequal length of the legs, right? So maybe because of some accident, the one leg is shorter as compared to the other. So the patient will have a problem in walking. So what do they actually do? For the smaller leg, they cut the bone part and they insert basically the telescopic link. Like so that telescopic arm is basically opened up or closed down few with the help of a magnetic field. So magnetic stimulus which can help to expand the leg. Now suppose the young boy is there which is going to on the growing part. So you can install the telescopic leg and then change the stimulus as a magnetic field, and we can think of the expansion as well as contraction of this type of link. So this is a typical example of a two-way programming. Then there can be a third category which is called the multi-stage programming, in which under the effect of some stimulus I am shifting some my material from state A to A1, then A1 to A2. The stimulus is different, then A2 to A3 another stimulus, and there can be n such stages. But the idea is at the end, with the effect of all the stimulus, the material
Hello, sir.
would come back.
Sir, you are not audible, sir.
Okay, still not audible. Is it not audible?
Sir, you are audible, sir. Audible to me at least.
Audible to us also, sir.
Okay, so what should I do then? May I continue?
Yes, sir. I think it might have been
Yes, sir. Yes, sir.
an internet
There
issue
might
from
be
their end.
problem with the individual, sir. It's mic or something, or speaker or something.
Oh, okay. So dear friend, please you can recheck or whatever. So I will continue again. Okay.
So we request you to continue, sir, please.
Okay. So the slide visible again?
Yes, sir.
Okay. So we were talking about the programming in the 4D part. So what we discussed right now is for the 4D part. As per the basic definition, there can be one-way programming, there can be two-way programming, or there can be multi-stage programming. I have to see which one is the best stimulus for me best and whether I am getting a repeatable result with these type of the programming. So the repeatability is actually important. The cycle should close. That is the basic funda in this type of programmable material, right? Okay, now let us see how we can go for development of these type of the programmable material with this. Okay, this is a one of the basic 3D printing process. I believe most of us are quite familiar with this 3D printing, which is called the fused deposition modeling. If there are some newcomers for this technology, let me explain it in a simple way. I have a thermoplastic spool, which is basically a polymer wire or a feedstock filament, which is a dark blue color. Now, this polymer filament is fed to the chamber like this. Now, there can be a different ways or a mechanism to feed this filament into this chamber. Like, for example, you can see the filament is fed through mechanical drives. Then there is a heating zone, right? So here I am having a heater which basically melt this wire, and on the other end there is a nozzle which basically reduces the dia of the wire, and I am getting a very fine wire out of this. So if you just do the Google and you want to buy these type of filaments or these type of processes, maybe from some e-commerce sites like Amazon or any other, you will see that most of the time I am getting a from the online sites the dia as 1.75, the most common available size, and it is available at the cost of rupees 1000 to 4000 5000 per kg, depending upon the grade of polymer I am interested. And but the another important thing is the dia of the filament, which is in most of the time is 1.75 mm, right? But otherwise, if you are interested, the size available are 0.4 mm to 4.0 mm. So I have a wide range, but most of the time, most of the commercial supplier make it in the size of 1.75 mm, right? So what the idea is, I have having a filament, feedstock filament. This filament is fed to this zone. Then there is a heating chamber. Basically, these filament wires, they have a melting temperature ranging from 150 to 300 for most of the commercial available polymers. And then from the other side, I am getting a very fine wire which is deposited layer by layer over this surface. So as the part is built, basically this platform lowers down and we get a 3D printed 3D printed component. Now some of you may have a query that why there are two different color wires. The answer is like in a printer like Stratsys you print, which is one of the pioneer in this area, and they hold the patent for this process till 2018. And they were having a very good technology in which suppose I am interested in some complex shape, some cantilever type shape. So what actually we do in that case, suppose I am making a cantilever and the material is extruded at the temperature of, let us say, 300. So I need some time to get it solidified. So for that purpose they provide a sport material, right? So this light color wire, light sky blue color, whatever you can say, is a sport material which works on a similar principle, but it is attached in a zone where this sport is required. Now, after the part is built, this sport material is normally water soluble, and the build material, which is actually the final part, this is the oil soluble part. So what we actually do is, after the fabrication of the component, we put it into a chamber. We call it as the ultrasonic chamber, in which I have to put the component in water with pH level more than 7, so that it is more on the alkaline side. Basically, what we do, we put the component in some detergent powder like Nirma or Wheel or whatever, so that the pH value is not toward the acidic side but towards the basic side. Then, and we raise the temperature around 65 degree and give some ultrasonic vibration to this, normally 30 kilohertz, and then in 10 to 15 minutes, my all this part, which is of the sport material is dissolved, and we get a very fine finished a polymer part that can be actually used for the functional as well as non-functional requirement. So now the idea is, if I want some polymer or some material to have a 4D property, I have to play with the either the internal property, intrinsic property of the material, or I have to reinforce, or I have to go for a metamaterial part. So one of the most convenient way is the reinforcement. So whatever the filament I am feeding through here, if I add some property into this filament, I can definitely control the 4D in a much easier and the cost effective way. That is the idea of working with these type of machine. Now I will show you some of the examples where we have used these type of process, and finally we were able to tune it for some advanced 3D or the 4D application. Now this was actually one of our initial work long back. We what we have done in this work was, we have a polymer of ABS, and we have a polymer of nylon, which is polyamide. PS6 is basically a nylon. 6 and 66, these are two extrusion grade nylon. This is a coating, this separate system used for the polyamide nylon. Only PS6 and 66, these two grades polyamide are extrusion grade, through which I can add some type of a reinforcement as per the literature. So once we were working in the development of these type of polyamide, one of our collaborator was from Jalgaon. He came to us that at his place there is a big problem of the banana fiber. Like in this Punjab Haryana region, we have a lot of prali problem. As agri waste. So in that part, specifically in Jalgaon, Maharashtra side, a lot of banana production is there. So they have a handling problem with the banana fiber. And we came across a paper by Behreen et al., in which the authors have recommended some steps to condition the banana fiber. So we used that paper actually and conditioned the banana fiber in such a way that we got some 100 micron dia and some length fibers are there, and we reinforced into the ABS and the polyamide, and we try to see the some 4D behavior for their thermal, mechanical and the morphological properties. So at the starting, we were not knowing how much proportion I must fix. Like we use at random the 5% reinforcement as per the explanation given in the Behreen et al. Paper. So some banana fiber length and dia were established, and we try to reinforce by weight of 5% in ABS and in the polyamide. Right. So this is the setup that was used. This is basically a twin screw extruder. In your screen, you can see this twin screw extruder is of a Thermo Fisher company. Right, this is a little costly extruder, mainly used in the pharmaceutical company, and I get a micro level or the nano level dispersion. So people are using the same extruder. We call it as a micro compounder also in the pharmaceutical industry for the mixing of the weight proportion of the salt for the making of the different tablets and all. So the main cost involved in this type of extruder is on this screw profile. You can see here are some screws over here. You can see over here in this picture, and there is a special thread profile around these screws, which is patented. And because of, so we worked on some of the parameters like nozzle temperature, nozzle dia, torque, and we were able to print 3D printer, and we were able to as per ASTM D638. And then once we put it on a UTM, we were able to break these components, and we try to explore what are the mechanical properties, what are the thermal properties. So in this particular diagram, this is really important for some of us. We are interested in establishing the thermal behavior of my material. Then from 250 to room temperature. Then also x-axis again, I have the time scale like 0 to 85. Suppose the experiment, about to run for this much period. And along the y-axis, what I am measuring, basically the heat capacity, how much energy in the heating cycle the material is absorbing, and how much energy in the cooling cycle the material is releasing. Basically, amount of the heat absorbed and amount of the heat retained there, then the material is considered to be thermally stable. Right. So to understand this, take one example. Suppose I go to the market and purchase two buckets, same color, same dimension, everything same. So kept on my rooftop. Another bucket is, in my bathroom. What we will observe, the bucket that is on the rooftop may develop crack soon, maybe in month or so. Whereas the bucket that is because of his having low percolation on it, right? So extra heating, excessive heating during the daytime, then let us say in some place the temperature variation is very high, so in the night time there can be extra cooling. So the amount absorbed, amount of heat absorbed and amount of heat released, if this is not within a range or not equal, I can say it develop so many cracks. Like for example, this ABS particular application is in the automobile, where the bumpers and the dashboard component all are made by these type of materials. You must be remembering there was one vehicle called taxi some few years back. During their earlier, when they basically launched this Tata Sumo during the earlier period, people were exploring like only the dashboard